Hey everyone, got a bunch of top tips and reminders for the upcoming A-Level Chemistry Paper 1. So these are just essentially a load of reminders of things to say about topics that are going to be tested on the paper. And some of the stuff I'm going to say is based around common mistakes I see, unfortunately, in student answers. Just simple little things that can eat away at your marks. The great thing is they're very simple things to put right. So the reason I make these videos is because I get messages like this, and if it worked for this person, there's absolutely no reason why it can't work for you. So the topic I'm going to start with is the ideal gas equation. So things to remember here, well obviously the equation is PV equals nRT, and you need to know your rearrangement. So let's say you ask for the pressure, it's going to be nRT over V. If you ask for the moles, it's going to be PV over RT, and so on. So know your rearrangements for the ideal gas equation. The units, pressure has to be in pascals. It's often given in kilopascals. The volume has to be in cubic meters. So if your volume's being given in centimeters cubed, you have to multiply it by 10 to the minus 6 or divide by a million. If the volume's being given in decimeters cubed, you've got to multiply by 10 to the minus 3 or divide by 1,000. R, the gas constant, 8.314, that's on the data sheet. So you don't have to remember that number, it's given. The temperature has to be in Kelvin. So if your temperature is being given in degrees C, to turn it into Kelvin, you add 273. Next topic we'll look at is bonding and structure. So there's quite a bit on this slide. So starting with metals and non-metals, they're going to have ionic bonds holding them together. So we need square brackets and charges. All ionic compounds have a giant ionic lattice structure. So that's the electrostatic attraction between oppositely charged ions. If you've got two or more non-metals, it's going to be covalent. So they're all held together by shared pairs of electrons. So in terms of structure, covalent lattices can be either giant or simple. So starting with giant covalent lattices, just a small number of substances have these. So boron, carbon, so diamond and graphite, silicon and silicon dioxide. And in those structures you've got covalent bonds holding the atoms together. All the rest are simple covalent lattices, so in those you've got intermolecular forces holding molecules together. Intermolecular forces can be different types, so you can have induced dipole-dipole forces, so they're also known as London forces. They exist between all molecules. You can have permanent dipole-dipole forces between polar molecules, and a special type of permanent dipole-dipole interaction is the hydrogen bond. So that's where you've got in the molecule a hydrogen directly bonded to a highly electronegative atom, fluorine, oxygen or nitrogen. So to have hydrogen bonds you must have an H directly bonded to an F, an O or an N. Very common thing we get asked to do is to draw hydrogen bonding. So when you're doing that, it must go from a lone pair on an F, O or N to the H delta plus on the neighbouring molecule. We need to be aware of the relative strengths of these intermolecular forces. So typically hydrogen bonds are the strongest, then permanent dipole forces, and the weakest are typically London forces. But we just need to be aware of the fact that London forces do get stronger with increasing numbers of electrons. And finally, if your substance only contains a metal, then it's going to be a metallic substance. So that's rows of metal cations, positively charged metal ions, surrounded by delocalized electrons. So in terms of the structure, metals have giant metallic lattice structures. So that's electrostatic attraction between those positively charged metal cations and the delocalized electrons. Moving on to melting point trends now. So when you're asked to describe melting point trends, maybe across a period, you've got to link to structure and bonding. So you need to talk about the particles involved and the attractions happening between them, and always include relative strength of attractions when you're doing a comparison. So I've got two slides for this, period 2 and period 3. So starting with period 2, you've got giant metallic lattices for lithium and beryllium. So their melting points increase. So beryllium's higher than lithium. That's due to stronger electrostatic attractions between the metal cations and the delocalized electrons. So there's the particles. There's an increase in charge going on. So lithium 1 plus versus beryllium 2 plus. You've also got a decreasing radius. So beryllium 2 plus is slightly smaller than lithium 1 plus. So because of those factors, more energy is needed to overcome the attraction in that metallic lattice. Moving on to the next two elements, boron and carbon. So they've both got giant covalent lattice structures. So you've got very, very high melting points for those. Large amount of energy needed to break the covalent bonds between the atoms. And finally, for nitrogen, oxygen, fluorine and neon, they've got simple covalent lattices. So very low melting points now due to weak London forces or induced dipole forces between the molecules, N2, O2, F2, or atoms of neon. So just to illustrate that, there's a graphic I found online, so you can see lithium, beryllium, so there's those two metals there, beryllium higher than lithium for the reason we've said here. Then you've got boron higher again, so these are your giant covalent substances, boron and carbon, carbon the highest, and then it drops. Really low melting points for the simple covalent molecules here. Moving on to period 3 now. So giant metallic lattices again, but now for sodium, magnesium and aluminium. So same idea as before. You've got increasing charge, more delocalized electrons and decreasing ionic radius. Therefore more energy needed to overcome the attraction in those metallic lattices each time. Silicon is the only giant covalent lattice in that period, so very high melting point, large amount of energy needed to break covalent bonds between the silicon atoms. And then we've got simple covalent lattices for phosphorus, sulfur, chlorine and argon. But you notice I've put some extra detail in there. Phosphorus actually forms a P4 molecule, sulfur S8, chlorine Cl2 and argon just individual atoms. So they've got relatively very low melting points compared to the others due to those weak London forces or induced dipole forces between the molecules. Atoms for argon. The intermolecular forces get stronger as the number of electrons increase. So we'll just talk about that on this graphic. So there's your three metals. Aluminium very slightly higher than magnesium, but you have got an increase there. Then it goes up significantly for silicon, a giant covalent substance. Then it drops for phosphorus, so that's simple covalent, but you can see it goes up for sulfur. S8, remember, so that's got more electrons in its molecule, so the London forces are stronger. Do not talk about breaking covalent bonds, that's not what's happening in these things. So phosphorus P4, sulfur S8, more electrons in sulfur, so therefore it has a higher melting point. Chlorine's only Cl2, so you can see the melting point dropped quite a bit there, and argon's just Ar, so it's very, very low there. Next topic we'll look at is polar and non-polar molecules. So the first thing we need to talk about is what causes dipoles in covalent bonds. So they're caused by a significant difference in electronegativity values of those bonded atoms. So typically anything greater than 0.4 of a difference will mean that the bond is polar. The only bond that you need to class as non-polar that has different atoms in is the CH bond, and that's because the difference is 0.4. So that's not significant. So the CH bond, even though it's different atoms, is classed as a non-polar covalent bond. So what causes the overall molecule to be polar or non-polar? Well, we'll start with symmetrical molecules. They're generally non-polar, and that's because the polar bonds are arranged in a way that the individual bond dipoles cancel each other out. So there's no overall dipole on the molecule. There's three examples for you: CO2, CCl4, SF6. So if you've got a non-symmetrical molecule, they are polar. And that's because the individual bond dipoles don't cancel out. So what causes a molecule to be non-symmetrical? So asymmetry is caused by the presence of different terminal atoms. So what do I mean by that? Different atoms around the central atom. So there's an example there, CCl3F. So you can see you've got 3 chlorines and a fluorine around the carbon. So that's going to be a polar molecule. The other thing that can cause a molecule to be polar is the presence of lone pairs around the central atom. So SO2 is polar. Remember, CO2 is non-polar. So SO2 is polar because there's a lone pair on the sulfur. Now there is one exception where you've got lone pairs around the central atom and the molecule is non-polar, and that's XeF4 xenon tetrafluoride. So there's a picture of it there. So you can see that the fluorine atoms are arranged sort of around the middle there in a sort of square plane away, and the 2 lone pairs that are on the central xenon, one's pointing up and one's pointing straight down, so their effects cancel each other out. So that molecule would be non-polar. So the next topic we'll look at is shapes of molecules. So molecular shape is determined by the number and types of electron regions around the central atom. Electron regions can be bonding regions and lone pairs. Bonding regions can be single, double and triple covalent bonds, and they are classed as one region each. And just be careful, don't call a multiple bond a bonding pair, because technically a double bond contains 2 bonding pairs of electrons and a triple contains 3. So always use the term bonding region. Lone pairs repel more than bonding regions. That's because they occupy more space around the central atom. And the repulsion order is the strongest is lone pair to lone pair, then lone pair to bonding region, and finally bonding region to bonding region. So when you're answering a question about shape and you've got to explain the shape, remember to say these things in your answer. So the first thing you'd say is what number and types of electron regions have you got around the central atom. So for example, you might have a total of 4 electron regions, and then you'd quantify them, 3 bonding, 1 lone pair. Next thing you talk about is repulsion. So is it equal or is it not? And if not, why not? So just remember, lone pairs repel more than bonding regions, and that repulsion order is at the top there. And then the last thing you would do is talk about the associated shape and the bond angle. So for the example above in the first bullet point, the shape would be pyramidal and the angle, the bond angle, would be 107 degrees. Where does that come from? Well, the starting angle for 4 regions is 109.5, but we need to subtract 2.5 degrees for every lone pair due to the extra repulsion. Next topic we'll look at is electron structure. Straight away I'm going to start with the most common mistake, students basically mixing up subshells and orbitals. So the rule is orbitals can only hold 2 electrons. There's 2 orbitals you need to know the shape of. So s orbitals, they have a spherical shape. P orbitals have what's called a dumbbell shape. So it's like a figure of 8. There's an upper part and a lower part, but both parts are the orbital. S subshells can hold 2 electrons. P subshells can hold 6 electrons. So that's where that common mistake comes from. I think as soon as a student sees P, they just think 6. But if it's the orbital, it's got to be 2. D subshells can hold 10 electrons. D orbitals, 2 electrons. F subshell, 14 electrons, but in F orbital, 2 electrons. And then when subshells fill up, the orbitals half fill first, and the spins go in the same direction. So you can see in the bracket there, I've got those 3 arrows, so that would represent a P subshell with 3 separate P orbitals, so the spins would be up, 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 all the same direction. And then you would start pairing them up. So you can see now it's up, down, up, down, up, down. And the last thing to say is the 4s subshell fills before 3d. Next topic we'll look at is ionization energy trends. So we'll start by saying what first ionization energy is. So that's the energy required to remove a mole of electrons from a mole of gaseous atoms. And you can represent that process by an equation like that. Just remember, the only state symbol allowed in ionization energy equations is G. Group trend, so this is applicable to all groups. First, ionization energy decreases down the group due to an increasing atomic radius, increase in shielding, so therefore weaker nuclear attraction for that outer electron that's removed. And even though there's more protons in the nucleus as you go down a group, the factors above outweigh the effect of the extra proton in the nucleus. Period trend, so all we need to worry about is periods 2 and 3. There's a general increase across these periods due to the extra proton in the nucleus, the same level of shielding, and a decreasing atomic radius. So because of that, there's a stronger nuclear attraction for that electron removed. So there's two anomalies in this period trend. So the first slight decrease in first ionization energy is for the group 3 element, so boron in period 2, aluminium in period 3. And that's because these are the first elements in the period with their outer electron removed from a higher energy p subshell. And then the other anomaly is for group 6, so oxygen for period 2, sulfur for period 3. These are the first elements in the period with electrons being removed from the p4 configuration. So you've got your first paired electron in a p orbital. So the paired electrons experience slight repulsion because they're in the same orbital, so slightly easier to remove. Moving on to successive ionization energy. So this is the first, then the second, then the third, and so on. So successive ionization energies for the same element always increase. So the second's always higher than the first, the third's always higher than the second, and so on. And that's due to an increasing proton to electron ratio. So remember, the protons are staying constant in the nucleus, but the electrons are getting one less each time. And finally, to establish what group an element's in on the periodic table from successive ionization energy values, you just need to look for the first big increase in ionization energy. And the electrons up to that increase are in the same outer shell. So if the big increase is between the third and the fourth, that means the element's got 3 electrons in its outer shell, therefore it's in group 3. Next topic we'll look at is enthalpy changes. So first thing we'll say is to calculate the delta H, the enthalpy change for a reaction from mean bond enthalpy values. I call it the in minus out method. So the energy in is the energy needed to break the bonds between the atoms in the reactants. The E out, the energy out, is the energy released when bonds between atoms are formed in the products. So you remember it this way, bendomic, so breaking is endothermic, energy has to go in. Making is exothermic, energy is released. Really common mistake in this is students saying energy is needed to make bonds. It is not. So energy is not needed to make bonds. It's an exothermic process. A reaction will be exothermic if the energy released is greater than the energy has to go in, and it'll be endothermic if the energy that has to go in is greater than the energy that comes out. If you're calculating the enthalpy change for a reaction from experimental calorimetry data, it's Q equals mc delta T. So the Q is the energy transferred to the surroundings. So often it's a solution in a beaker or water in a beaker. You then, once you've got your Q, you change that into kilojoules, and then to get delta H, the Q in kilojoules is divided by the moles involved in the reaction. The M in the mc delta T calculation is the mass of the liquid that the thermometer's in. Often students pick the wrong mass. So wherever the thermometer is, that's the mass we use in Q equals mc delta T. Delta H values from experimental calorimetry results will often be different to the data book values. They're often a lot lower, and that's due to heat loss to the surroundings, the reaction not being carried out in standard conditions in the lab, incomplete combustion if you are combusting alcohols, and the specific heat capacity of the apparatus has been ignored. When you're calculating enthalpy changes for a reaction using combustion data, it's reactants minus products, and the way I remember that is crap. If you're calculating delta H for a reaction using formation data, it's products minus reactants. and I remember that using the word faux. Don't forget to multiply delta H values by the number of moles in the equation. And delta H values must have a sign. So it's either positive if it's endothermic or negative if it's exothermic. So remember, when you're doing the calculation, your calculator will not put a positive sign in front of your final answer. Obviously, for an endothermic reaction, don't forget the positive sign. Obviously, if it's negative, the calculator will put the negative sign in for you. Moving on to enthalpy changes of neutralization. So that's the enthalpy change for a reaction between an aqueous acid and alkali to form 1 mole of water. So in other words, we're talking about this reaction, H plus ions plus OH minus ions, obviously aqueous, making a mole of H2O. The enthalpy change of neutralization for all strong acid-alkali combinations is around the minus 57 kilojoules per mole mark. And that's because basically all strong acids and alkalis involve the ionic equation that's directly above. And for weak acid-alkali combinations, the enthalpy change of neutralization is less exothermic than minus 57 kilojoules per mole because these are only partially ionized, so some of the energy is being used to ionize the acid or alkali. If you're devising a calorimetry experiment to determine the enthalpy change of neutralization, it's best to go for concentrations and volumes of the acid and alkali so the moles of the ions are the same. And in terms of concentration, it's best to use either 1 or 2 moles per decimeter cubed, nothing lower, nothing higher, so you get a decent temperature rise that can be recorded. So moving on to the calculation, same as before, Q equals mc delta T first. That gives you the energy change in joules for the reaction. Change it straight away into kilojoules. The M is the mass of solution, and it's the combined volumes of the acid and alkali. So if you use 35 cm cubed of each chemical, then the mass of the solution is going to be 70 grams. The delta H is the Q in kilojoules divided by the moles of water formed. Remember, in the definition, it's the enthalpy change per mole of water formed. So we divide by the moles of water. And don't forget your sign, but this one is always negative because neutralization is an exothermic reaction. Sticking with enthalpy, we'll look at Born-Haber cycles now. So state symbols are absolutely essential in Born-Haber cycles. Don't forget to include electrons. Often students forget to include electrons when it gets to the ionization energy stage. If there's 2 moles of something in a cycle, don't forget to double the enthalpy change because enthalpy changes are per mole. And remember, you can only perform 1 change per step. Arrow direction, so a downwards arrow in a Born-Haber cycle is for an exothermic process, and upwards arrow is for an endothermic process. For enthalpy change of solution cycles, make sure you can draw both types. So there's an exothermic one and an endothermic one. But in terms of the calculation, doesn't matter what type of cycle it is, enthalpy change of solution is always the sum of the enthalpy changes of hydration minus the lattice enthalpy. Both lattice and hydration enthalpies are affected by ionic radius, not atomic radius, and ionic charge. The smaller the ionic radius, the more exothermic the lattice and hydration enthalpies will be. And finally, the greater the ionic charge, the more exothermic they'll both be. Next topic we'll look at is entropy. So entropy is the dispersal energy in a chemical system. And to calculate delta S, the entropy change, it's products minus reactants. So I remember that with the word SPA. The Gibbs equation, delta G equals delta H minus T delta S. And remember, entropy S is measured in joules per mole. So that can cause problems because delta H and delta G are often in kilojoules per mole. So if the units for delta G in the question are kilojoules per mole, you need to change your delta S into that by dividing it by 1000. And remember, temperature in the Gibbs equation must be in Kelvin. A reaction is feasible at a particular temperature if delta G is negative, and to calculate the minimum temperature at which a reaction becomes feasible, you set delta G equal to 0, so the Gibbs equation becomes T equals delta H divided by delta S. And then often asked at the end of an entropy question, suppose you've calculated that the reaction is thermodynamically feasible, delta G is less than 0 at a particular temperature, why mightn't it still go? That's because the activation energy is too high. Next topic I look at is redox. So when you're writing half equations, if it's acidic conditions, you balance the atoms using H plus ions and H2O. If it's alkaline conditions, use OH minus ions and H2O. So once all the atoms are in, we balance for charge left and right using electrons. The charge must be the same on both sides. Remember that the total change in oxidation number is equal to the number of electrons involved in a half equation. So if you've got manganese going from plus 7 down to plus 2, it's obviously gained 5 electrons. When you combine half equations to generate the redox equation, your electrons must cancel. So that's where you multiply out half equations to make the electrons the same on each side, and then when you add them together they're going to disappear. And don't forget to cancel like terms on either side of the equation, and they will often be H plus ions, OH minus ions and H2O. Sometimes you are supplied with a redox reaction equation, you've got to balance it. That's often tricky using trial and error. So oxidation number method makes it much easier, and remember the golden rule for that is the total change in oxidation number for the reduction process must equal the total change in oxidation number for the oxidation process. So we'll move on to redox titrations now. Just a couple of quick slides for this. So the great thing is you will always be given the equations. You don't have to remember the redox titration equations. So for example, there's an equation there. You're not expected to remember that. Now sometimes there's more than one equation involved in a process. I'll give you an example in a second. So when that's the case, you can't apply a mole ratio across two different reaction equations. So the classic example is the iodine thiosulfate titration. So there's two equations involved in this process. First one generates the iodine, so there's an example of iodine being generated, and then once the iodine's generated you do the titration with sodium thiosulfate of known concentration. So you can see iodine is in both of those equations, and the golden rule is they are the same thing. So I'll just illustrate that with some numbers. So let's suppose you worked out that you've used 0.02 moles of thiosulfate in the titration. So obviously we're going to half that to get the moles of iodine. But look, that 0.01 has appeared here. Even though there's a 3 in front of that in the first equation, these are the same thing. So you can't apply a mole ratio across two separate reactions. So now we know the moles of iodine. We then apply the mole ratio in this first equation, and that gets you the moles of the IO3 minus in this case. Alternatively, you could just multiply out this second equation. So you do have a 3 in front of the I2. If we put those numbers in again, 0.02 thiosulfate, we're still going to half to get the iodine. We're still going to get to the same final answer there. And then the final thing to look at is when do you add the starch indicator. So I've got a sequence of photos from experiments we've done. So start of a titration, your flask's going to look that reddy brown colour because there's iodine in there. As it's reacted away with the sodium thiosulfate, it loses its colour, so it gets paler. So at that second photo where it's sort of a pale yellow colour, almost all of the iodine's been reacted. You then add starch indicator, and you can see the third picture there, it's gone like a blue-black colour, and then it's really easy to see the end point, blue-black to colourless when all the iodine's gone. The reason why we do that is because obviously that's just going to get more and more pale yellow. It's very difficult to see when the palest of yellows goes to colourless. So we use the starch to kind of intensify the colour, get that blue-black colour there. So we'll move on to standard electrode potentials now. It's quite a lot on this slide. So first of all, standard electrode potential half equations are conventionally written as reduction processes. So gain of electrons. Electrons are on the left. The oxidizing agent, the electron acceptor, is the species or combination of species on the left-hand side. The most powerful oxidizing agent is the species or combination species on the left, but they've got to have the most positive standard electrode potential. So obviously that's going to be supplied in a table. And then moving on to reducing agents, they are electron donors. So they are the species or combination of species on the right now. And the most powerful reducing agent is the species on the right with the least positive standard electrode potential in the table. Now, often you have to construct the overall cell reaction. So that's when you combine the two half equations together from the two systems. So the half equation with the most positive electrode potential moves forwards, accepts the electrons. The one that's the least positive moves in reverse and donates electrons. And remember, the electrons must cancel, so you might have to multiply out one or both of the half equations to make that happen. The most positive electrode potential is the positive electrode in the cell. Least positive is the negative electrode. And then to calculate the voltage of the cell, or the E cell, it's most positive electrode potential minus least. And just remember that if a half equation did need to be multiplied out to balance the electrons, you don't multiply out its electrode potential value. If you've been asked to draw the cell that's used to measure the electrode potential value, then it's the one where you draw it alongside the standard hydrogen electrode, so make sure you know how to draw that. The salt bridge allows a flow of ions, remember, so that's typically just a piece of filter paper soaked in an electrolyte. So the classic example is potassium nitrate. So it allows the K plus ions and NO3 minus ions to flow into the beakers to balance out the charge difference that builds up. And just remember, when you draw in the diagram, that your salt bridge actually goes into your solutions. Last couple are about fuel cells and storage cells or batteries. So fuel cells, remember, have reactants supplied continuously to the cell, whereas a storage cell or battery, the reactants have to be stored within the cell. And finally on this slide, standard conditions, remember, are temperatures 298 Kelvin, or you could say 25 degrees C, pressure 100 kilopascals, and any solutions must be at 1 mole per decimeter cubed. Next topic we'll look at is acids, bases and buffers. So first of all, the Bronsted-Lowry definitions. An acid is a proton donor, a base is a proton acceptor. Conjugate acid-base pairs, there must be an acid and a base on each side of the equation, and there must be one from each of the pairs. Conjugate acid-base pairs, the only difference between the species is an H plus ion, so they can easily transfer into each other by transfer of a proton. If you've been asked to write the Ka expression for a named weak acid, you must include all of the species. You can't give the H plus concentration squared version of the Ka expression. What does Ka mean? Well, it's a measure of the amount of dissociation. So the greater the Ka value for a weak acid, the stronger it is, the more dissociated it is. And in terms of pKa, the smaller the pKa, the stronger the weak acid. To calculate the pH of anything, you need to know the hydrogen ion concentration, and then once you've got that, you do minus log. To calculate the H plus concentration of a strong alkali, we need to use the Kw expression. So that rearranges to H plus concentration equals Kw divided by the hydroxide ion concentration. Just remember or beware if it's a dibasic alkali. If you've got, say, 1 mole per decimeter cubed calcium hydroxide solution, CaOH twice, you've actually got 2 moles per decimeter cubed of hydroxide ions. You've got to calculate the H plus concentration of a weak acid. It's the square root of Ka times the HA concentration, the original concentration of the acid, and I refer to that as the square root of Ka equation, just to remember that one. And to calculate the H plus concentration of a buffer, I remember it as acid over salt. So Ka multiplied by the acid concentration divided by the salt concentration. If you add a small amount of water to a buffer, the pH will stay the same, and that's because the ratio of the concentrations, so the acid to salt concentration ratio, has stayed the same. And finally, when you're explaining how a buffer works, you must talk about the actual species. Don't just refer to the weak acid or the salt ion. Actually bring in the name or the formula of the actual species. Quick slide about the blood buffer system. So blood pH is carefully controlled by a buffer system to have a pH of 7.40. So what's the blood buffer made from? It's made from carbonic acid, which is a weak acid, and the hydrogen carbonate ion, which is the salt ion of that weak acid. There's the equation that represents the system, the blood buffer system. And if you add a small amount of acid to the buffer system, you're increasing the H plus concentration. So that store of, or reservoir you could call it, of HCO3 minus ions will react with the H plus ions and send the equilibrium over to the left, and that'll sort of restore the pH. And if you add a small amount of alkali to the blood buffer, that's going to react with the H plus ions, so decrease the H plus concentration, and therefore the reservoir, the store of H2CO3, will dissociate more to replace the lost H plus ions. Equilibrium shifts right, and the pH of the blood is maintained. Final slide on this topic is about pH titration curves. So there's just a very rough sketch that I've done with the three curves. I'll just explain the different colours. So the pink one is the strong acid, strong alkali combination, so something like hydrochloric acid with sodium hydroxide. The blue one is strong acid, weak alkali, so something like hydrochloric acid with ammonia or ammonium hydroxide. And the green one is weak acid, strong alkali, so something like ethanoic acid and sodium hydroxide. The centre of the vertical section is what we call the equivalence point. So that's when you've got the equivalent moles of acid and alkali present as determined by the mole ratio of the equation. The vertical section in a pH curve tells you the end point of the titration. So in other words, the volume of acid or alkali that's needed from the burette. And remember, it's typically one drop from the burette that causes that rapid rise in pH, that vertical section. So if you have to choose a suitable indicator for a titration, normally they'll give you a table of indicators with pH range values. You just need to make sure that the range of the indicator, the pH range of the indicator, lies in the vertical section. So a couple of examples. So phenolphthalein, you can see that that would be fine for the pink curve, and it would also be fine for the green curve, but it would be no good for this blue curve, because it's kind of changing colour after the neutralization's taken place. And another example for you, methyl orange is okay for the pink curve, it's okay for the blue curve, but it's changing colour here. And we don't want that, obviously, because the endpoint would be far too low. So there's a couple of examples there. You don't have to memorise any indicators, you'll be pleased to hear. You would always be supplied with the information, but you just need to know how to apply it. Next topic is reaction rate. So I think there's 3 topics left to go. This one, equilibrium and transition elements. So stay with it. Right, so reaction rates. So when you're establishing orders of reaction using initial rates data, so those rates tables questions, don't forget to say which experiments you're using. So you could say something like this: from experiments 1 and 2, the concentration of A has doubled, the rate has doubled, therefore it's first order with respect to A. You've got to be really clear about which experiments you're using and what that's telling you. If you're calculating the rate constant K, always include the units. They've stopped asking for units, but they still want to see them. And when you're calculating rate constants, just have a quick check in the column headings of the table that there's none of this times 10 to the minus 3 or times 10 to the minus 6 going on in the heading. All the data in that column, in this case, would be multiplied by 10 to the minus 3. Moving on to reaction mechanism. So for reaction mechanism to be valid, the species in the rate equation must be the reactants in the slowest step, or the rate determinant step, RDS for short. The order tells you how many moles you need in the equation. And then the other thing you've got to do is the sum of the steps must give the overall reaction equation. So when you are adding the steps together, it must cancel down to the overall reaction equation. And just make sure that all of your equations balance for atoms and charge. So the charge needs to be the same on each side of the equation arrow. If you're given a concentration time graph and you're asked to determine the order of reaction, calculate 2 or 3 half-lives. They don't have to be consecutive ones, and it's very likely that it will be first order. So you need to just show that there's a constant or approximately constant half-life. Whatever you do, don't mix up concentration time graphs for rate concentration graphs. Make sure you know all the shapes for those. A couple of things about Arrhenius plots. So the first thing to talk about is the gradient or negative gradient is equal to minus EA over R. The minus signs will obviously cancel. So EA activation energy would be found by multiplying the gradient by the gas constant R. Remember, the activation energy is never negative, and the activation energy from an Arrhenius plot is measured in joules per mole, not kilojoules per mole. If the x-axis starts at 0, the y-intercept is the ln of A. So to get A, it would be e to the y-intercept. If the x-axis does not start at 0, you can't say the y-intercept equals ln A. Still with rates, but moving on to Boltzmann curves, the axes labels, the y-axis is the number of particles or number of molecules. The x-axis is the energy or kinetic energy. Your curves must start at the origin because there's no particles that have 0 energy. And the curve must not cross the x-axis at high energy. It has to asymptote because there's no limit to the amount of energy a single particle could have. The total area under a Boltzmann curve is the total number of particles or molecules in the sample. And the area under the curve after or to the right of the activation energy shows the number of particles with sufficient energy to react. Catalysts lower the activation energy, so they will increase that area under the curve to the right of the activation energy, so more particles will have sufficient energy to react. And we'll just talk about the different temperature curves. So lowering the temperature, the curve will shift to the left because the particles have got less energy. The peak gets higher, so it kind of bunches up on the left-hand side. And then if you increase the temperature, the curve will shift to the right because the particles have got more energy now and the peak of the curve is lower. So I know you'll have seen this hundreds of times before, but here's a picture with all of that on. So you can see the curves are both starting at the origin and it's asymptotes at the high energy. There's your activation energy without a catalyst with the smaller areas under the curve to the right of the activation energy. The green dotted line, the catalyst activation energy, so it's much lower now, bigger area under the curve to the right. So that red curve's the warmer sample, so it's all shifted to the right, peaks lower, and the blue curve shifted to the left and a higher peak at that colder temperature. Second last topic now, equilibria, so Kc and Kp. So in terms of expressions, it's always products on the top divided by the reactants. Square brackets for Kc expression, so that means equilibrium concentration in moles per decimeter cubed. Curved or no brackets for Kp. And if you're calculating the equilibrium constant, you must always give the units. Kp expressions only include gaseous species. If Kc or Kp is greater than 1, the equilibrium position is to the right or on the product side of the equilibrium. If it's a double greater than sign, it means it's significantly on that side. And then the opposite, if it's less than 1, equilibrium positions to the left, so on the reactant side, and the double arrow significantly so. A couple of checks you can do during Kp calculations. So partial pressures should always add up to the total pressure, and the mole fraction should always add up to 1. And remember, the value of Kc and Kp is only altered by changes to the temperature. So if you do change the temperature, the reactant and product concentrations or partial pressures have to change to give the new value of the equilibrium constant, and that's achieved by an equilibrium shift. And I thought we'd never get here, but we're on the last topic now, transition elements. So a transition element forms at least one ion with an incomplete d subshell. Scandium and zinc are not transition elements, and that's because scandium only forms the Sc3+ ion, so it doesn't have any d electrons at all. Zinc only forms the Zn2+ ion, so that's got a 3d10 configuration, so it doesn't have a partly filled d subshell. Sticking with electron configuration, remember copper and chromium are unusual because they have a 4s1 configuration rather than the normal 4s2 for all the others. When any transition element forms an ion, so they always form positive ions, lose electrons, but they lose electrons from the 4s subshell before any come out of 3d. General properties now, so as well as the usual metallic properties like conductors of heat, conductors of electricity, they have these 4 general properties: variable oxidation states, they form complex ions, they form coloured compounds, and they can act as catalysts, and catalysts can be homogeneous or heterogeneous. A little bit about reactions now. So all aqueous transition metal ions, so there's an example there, CuH2O6 2+, they all produce hydroxide precipitates when you add a small amount of aqueous hydroxide ions. Only the chromium 3 hydroxide precipitate dissolves in excess, and that gives that ion there, CrOH6 3-. You get the same reaction taking place when you add aqueous ammonia, because effectively you're adding ammonium hydroxide. So all aqueous transition metal ions produce hydroxide precipitates with a small amount of aqueous ammonia, and this time 2 of them dissolve in excess, so that's copper 2 hydroxide and chromium 3 hydroxide again, and there's the respective products there. Last thing on this slide, know your colours. I know it's a pain, but you really do need to know all the colours of the transition metal ions. So moving on to isomerism in transition element complexes. So we'll start with 4 coordinate complexes. So these are the ones of platinum. Just got to remember that they are square planar. So we've got cis and trans platin. So you can see here that in the cis version, the identical ligands are 90 degrees apart, whereas in the trans version, they are 180 degrees apart. Moving on to 6 coordinate complexes. So the first thing you do is start with an empty octahedron. So that's that new diagram there. You would then attach your ligands via the correct atom. If you've got 3 bidentate ligands, complexes will show optical isomerism. So you would just show the mirror image of whatever you've drawn. If you've got 2 monodentate and 2 bidentate ligands attached, the trans version, so that's where the identical ligands are 180 degrees apart, they don't show optical isomerism. However, the cis version, so that's when the identical ligands are 90 degrees apart, they do show optical isomerism. So you'll be pleased to hear that's it. Congratulations to anybody who's actually still listening. I hope you found that helpful. So all that's left for me to say is good luck on June the 10th. You're gonna smash it.